Welcome, crew. These are our 10.1b notes, so our second notes on power functions, where we're going to talk specifically about how to find the equation of a power function, and we're going to talk about power functions and variations, specifically direct and inverse variation. So let's go back to our definition. A power function is a function that can take the form of y equals k times x to the p, where k and p are constants so long as p is not 0. That would make our function a constant function, or 1, which would make our function a linear function. So here are some examples. I have f of x, and I can rewrite this. We did this in our last note as 2 over 27 x to the 6th to the 1/3, which would be 2 over 27 to the 1/3 times x to the 6th to the 1/3. Right. We can simplify that, and that gives us 2 over 27 to the 1/3 is the cubed root of 27, which is 3, times x to the 6th to the 1/3, which if we multiply those exponents gives us x to the 2nd. So pulling the constants, the coefficients out, that's 2/3. Bringing the x to the top, I get 2/3 x to the negative 2nd, k times x to the p. This one is not a power function because my base is more than x. This is a polynomial function. Okay, so nothing new there. We need to be able to identify a power function when we see it. One term, power with a coefficient where x is in the base. Now, let's look at how to find the formula of a power function. We're going to do this very much in the same way, at least start it, that we found the formula for an exponential function. So here's our first example. We want to find a power function, which means we're looking for an equation of the form y equals k times x to the p. And we're given 2 points, 6, 17, and 1, 2. So we're going to take the point 6, 17, and we're going to plug those in for x and y. So that's going to give me 17 equals k times 6 for x to the p. And we're going to take the point 1, 2, plug those in, and I get 2 equals k times 1 to the p. Now, I could divide both of these equations like I did with exponents, but if I look at this second equation, 1 to any power is always 1. So that equation tells me simply that 2 equals k times 1. I know that k is 2. If I now take this along with my first equation, then I get 17 equals 2, which I now know is k, times 6 to the p. If I divide both sides by 2, I get 17 halves equals 6 to the p. Trying to solve for that exponential equation, we're going to take the ln of both sides. That gives me, right, bringing the exponent in front of the log, p times the ln of 6 equals the ln of 17 over 2. Dividing both sides by this ln of 6, I get that my p is equal to the ln of 17 over 2 divided by the ln of 6. That's my exact answer for p. If I stick that in my calculator and let it help me evaluate that, I get a better sense of its size, and I get p is about 1.194. So, trying to get a formula, I can now say that therefore, right, my power function will be of the form y equals my k, 2, times x to my exponent, which is about 1.194. And there's my formula. Okay? So, not anything new. We've done all this before, just applied to a new type of function. Let's do another one. So here I want to find a possible power function. So again, I'm looking for an equation of the form y equals k times x to the p, given that g of negative 6 equals 36. So that is a point, right? That's the point, negative 6. When x is negative 6, y is 36. So I plug that in, and I get 36 equals k times negative 6 to the p. I also know that g of negative 2 is 4/3. That's the point, negative 2, 4/3. So we're going to plug that in, and we get 4/3 equals k times negative 2 for x to the unknown p. Okay, this one isn't quite as friendly with me as the other one. So we're going to come in here and we're going to divide both sides. So when I divide both sides of this equation, right, I get 36 to divide by 4/3. I'm going to flip it and multiply instead, so times 3/4 equals, my k's will divide out, and I have this situation where I have a negative 6 to the p over a negative 2 to the p. Well, let's do this first. 4 will divide into 36 9 times, and I get 9 times 3 is 27. And I'm back here where we were last time, where if you'll remember, we had our rule of exponents that said if we're dividing two numbers and we raise that fraction to an exponent, we can distribute that exponent to the top and the bottom. So that's a to the n over b to the n. And this looks a lot like this, so we're going to take it back and we're going to rewrite this by undistributing that exponent, and I get negative 6 over negative 2 to the p. That gives me 27, right? Simplifying this equals 3 to the p. Now, I could take the ln of both sides here, but again, we're going to be intuitive here. And as you think about this, I'm looking for the exponent I would put on 3 to give me what would equal 27. Well, isn't 27 3 to the third? So that would be 3 to the third equals 3 to the p. And by the property of equal powers, if I have two powers that are equal and their bases are equal, then their exponents will have to be equal. So that tells me p would have to equal 3. So that's p equals 3. What I don't have yet is k. So let's come back now, and let's take that p equals 3 along with one of these two equations. And I think I'm going to take the bottom equation. Well, the top equation doesn't have any fractions, but it's got smaller numbers. Let's take the top one. So I'm going to take the top equation along with this p equals 3, and I get 36 equals k times negative 6 to the 3. So that is 36 equals k. Negative 6 times negative 6 is 36, times negative 6 again is negative 216. So dividing both sides by negative 216, I get k equals 36 over negative 216, which reduces to negative 1/6. Okay, so therefore, my equation, g of x, will equal my k, which is negative 1/6, times x to my p, which is 3. Okay. So I'll bet you can do that. You guys are so smart, and I think you'll be well with that. Let's take another step in this process, and we're going to look at this function, g of x. So this is g of x, and I'm told that it's a power function, so I know its equation is going to be of the form y equals k times x to the p, and it's a mystery. I don't have the equation. So one thing I can look at is that this function has end behavior up, down, and it has the shape of an odd-powered function. So one thing I know is that p is going to be negative because it's flipped. Okay, now that's going to show up in our work, so you may or may not recognize that. It's okay. Let's look at what happens after this. So if we learn that the point negative 1, 3 lies on the graph, does that give us enough information? Well, if I have the point negative 1, 3, and I know that I have a power function, so that's y equals k times x to the p, then I know that 3 equals k times negative 1 to the p. So what I know about negative 1 to the p is that if p is even, negative 1 to an even power will equal 1. But if p is odd, negative 1 to an odd power will equal negative 1. So at this point, because I don't know what k is, I really don't know anything. So at this point, I have no conclusion. I'm going to need another clue. Okay, so let's go on, and we're going to pick up another clue. So now we're told that we also have the point 1, negative 3. So let's come back to where we were, right? We had the point negative 1, 3. And again, that gave us 3 equals k times negative 1 to the p. And now we have the point 1, negative 3, which gives us negative 3 equals k times 1 to the p. If we take these two equations and divide them, that gives me negative 1 equal, my k's divide out, and I get negative 1 over 1 to the p when I undistribute that exponent. Well, that tells me that negative 1 equals negative 1 divided by 1 is negative 1 to the p. Well, that does give me some information, right? What I can get from here is if negative 1 to the p is negative, then p is odd. We had that hint from the graph earlier. Now we've proven it. We know it's true. All right. So now let's add another point. What if we know that the point 2, negative 96 is on the graph? Well, if we take 2, negative 96, and we plug that in, then we get negative 96 equals k times 2 to the p. And if we take that along with one of our other points, let's take the point negative 1, 3, then now we get 3 equals k times negative 1 to the p. And if we divide these, then that gives us negative 96 divided by 3 is negative 32. K's divide out, undistribute that exponent, and we get 2 over negative 1 to the p, which is negative 32 equals negative 2 to the p. And like we did earlier, this negative 32 is familiar. We would have trouble taking the ln of both sides here because we're not allowed to take the ln of a negative. We could finagle that, right? But what's maybe a little easier here is to recognize if we take negative 2 and raise it to the 5th, that gives us negative 32. So if that equals negative 2 to the p, right, then those exponents have got to be equal and p equals 5, right? So now we know what p is, and if we come back with one of our equations, right, so let's take this equation along with our value of p, right, and bring those together, then we get 3 equals k times negative 1 to the 5th. That's 3 equals k. Negative 1 to an odd power is going to be negative 1. Dividing, I get k equals negative 3. So now I know my equation, right? My equation, therefore, is that g of x equals k negative 3 times x to the 5th. Last part of this question. Well, I thought there was a last part to this question. I missed it here, is to state 3 other points which also lie on it. So for that, we're going to start with our equation that g of x equals 3 times x to the 5th. And we're going to plug in just whatever x's we want. If we were to plug in g of, say, negative 2, we would get 3 times negative 2 to the 5th, which is 3 times negative 32, which is negative 96. So we have the point negative 2, 96. We had the point 2, negative 96, and the point negative 2, 96. Those seem to have a relationship, and we had the point 1, negative 3, and negative 1, 3. Similar relationship, right? If we wanted two other points, we could plug in another number for x, so we could plug in, say, g of 3, and we would get 3 times 3 to the 5th, which would give us 3 to the 6th, which is 729. And following our pattern, if the point 3, oh, sorry, this was a negative 3, so that makes that negative 729. If we have 3, negative 729, then we also have the point negative 3, positive 729, and that follows this being an odd function. Okay, so those are the basics of writing an equation. Let's go on and apply, let's go on and talk about direct and inverse variation. Okay, a power function is a type of direct variation function. This is something you'll often see on an SAT or an ACT question, and students often come and they say, oh, Mrs. Key, I didn't know how to do this. And I come back and I say, well, we learned it, but it was just so easy that we didn't have to spend much time on it. And what we don't spend a lot of time on, we tend to forget quickly. So you might want to pay attention to this. And here's the idea. If a quantity, right, we're going to say y, is directly proportional to some other quantity, well, q, then the relationship is that y equals k times 2. So whenever you see this directly proportional, that means that you're going to multiply by a constant. If a quantity y is directly proportional, right, you're going to multiply by a constant, to a power of x, then you're going to multiply by that power of x. So y would equal k times x to the n. Here's an example. The area of a circle is proportional to the square of its radius. So I have a quantity, the area of a circle. Let's call that a. Is proportional to, right, the is means equal, proportional to means we're going to multiply by k. The square of its radius, let's call the radius r, and we'll square it. So that gives us that a equals k times r squared. Here's another one. The thrust T, that's a quantity, right, and that's the thrust delivered by a ship's propeller, is, that's equal, proportional to, we're going to multiply by k, the square of the propeller's rotation speed, r, so that would be r squared, times, right, we're going to multiply by the fourth power of the propeller's diameter, d. So that's d to the fourth. That gives us that T equals k times r squared times d to the fourth. Sounds complicated, but we're just reading and interpreting into math. All right, let's talk about inverse variation. If a quantity y is, right, is means equals, so y equals, inversely proportional to, when you see that, that means you're going to divide by k instead of multiply by k. No, I'm sorry. Is inversely proportional means that you're going to take your constant and then divide, okay? By a power of x, that means that you're going to divide by that x to the n. So you get y equals k over x to the n. Here's an example. The weight of an object w, so the weight of an object w is, right? So that's equals. We have w equals. Inversely proportional to means that we're going to take k and we're going to divide it by the square of the object's distance d from the Earth's center. So that's w equals k divided by d. So we have this equation, w equals k divided by d. An object weighs 44 pounds on the surface of the Earth. So that's its weight, which is about 3,959 miles from the Earth's center. That's a value of d. Right? The question is, at what distance from the center of the Earth, so this is saying find d, Will the same object weigh 19.2 pounds? That's a value of W. Well, we're going to need to find K, so we're going to take the first piece of information that the weight is 44 when the distance is 3,959 miles. If we take that and we multiply both sides by 3,959, then we get that K is equal to this product hold on. I missed something important. This said that it was inversely proportional to the square of the distance. So I need a squared here, which puts a squared here, which means I've got to square this, which means that we have to multiply by that squared. Ooh. Okay. So now we get a value of K that is 689,641,964. So now if I want to find D, when the object would weigh 9.2 pounds, I'm going to come in here and I'm going to say 19.2 will equal this 689,641,964, that's my K, divided by my distance squared. I'm trying to solve for something that's in the denominator, so I'm going to multiply both sides by that distance squared. That will divide that out. And then I'm going to divide by that 19.2. So that's going to give me distance squared equals 689,641,964 divided by 19.2. So from there, I'm trying to solve for D, not for D squared. So from there, I would come in and I would take the square root of both sides of this equation. That's going to give me D alone, since D can't be negative, right? I don't have to consider the negative, right? Evaluate this in my calculator, and I get 5993.234, and that would be in miles. So that answers my question using my power function. Okay. One more example here. We have a volcano that erupts in a powerful explosion, and the sound of the explosion is heard in all directions for many hundreds of kilometers. And we have that the speed of sound is about 340 meters per second. So let's kind of think about this. We know that the speed of sound is about 340 meters per second. Well, in this table, I've got my distance in kilometers, so I'd rather this be in kilometers, so we can do that by dividing by 1,000, which gives me 0.340 kilometers per second. So that means that if 5 seconds has passed, then my distance is going to be 5 times this 0.340, which gives me about 1.700 kilometers. If I put in 10 seconds, then I've got 10 times 0.340, which is going to give me about 3.4 kilometers. If I have 1 minute, then that would be 10 times, that would be 60 times 0.340, which would be about 20.400 kilometers. And if I put in 5 minutes, then I'm going to do 300 times 0.30, and that gives me about 102 kilometers. So this gives me the distance that that explosion has traveled as a function of t, and we want to write a formula for d as a function of t. So d as a function of t, right, took our time t and multiplied it by 0.340, right? So we get that for our function of d. B says, how long after the explosion will a person living 200 kilometers away hear the explosion? So in that is asking me to find t when d is 200. So I have an equation, and I plug in 200 for d equals 0.340t. Divide both sides of this equation by 0.340, and that gives me that t is equal to about 588.235 seconds. If we divide that by 60, then that's about 9 minutes and 48 seconds. Okay, a little more than 9 minutes. All right, now C asks us to find the land area. Well, we know that this volcano, if it erupts here, and that sound goes off in every direction, then the area would be the area of this circular region around it. And we know that area of a circle is equal to pi times the radius of the circle squared. Well, the distance that this travels is our d, so that this would be pi times d squared. So if I am going to write a as a function of t, right? This is not t, but I have d as a function of t, then I can substitute that in, and I get that a of t will equal pi times what d equals, which is 0.340t, which has to be squared. If we simplify that, right, by squaring the 0.340, we get 0.116 pi times t squared. D says that the average population density around the world is 31 people per square kilometer. Well, this area is in kilometers squared, right? And we're supposed to write a formula for P as a function of T, where P is the number of people who heard the explosion. So the number of people who hear the explosion would equal 31 times the area that is covered. So that's going to be P in terms of T will equal 31 times my area in terms of T, which was my 0.116 pi times T squared. If we multiply these two numbers together, then we get 3.584 pi times t squared. It's a decimal point there. So finally, E says, how long will it take until 1 million people have heard the explosion? So for E, I'm supposed to find t when my number of people is 1 million. So if I take the equation that we just found, we would get that 1 million will equal 3.584 pi t squared. And to solve that for t, right, we would divide by this, so we would get t squared equals 1 million divided by that, which gives me 88814.142. Take the square root of both sides, and I get that t is about 298.017 seconds. which is almost 5 minutes, a little under 5 minutes. Okay, so you're going to do a problem similar to this one in your work as well, and I think that's it for us. See you